Okay, so thanks a lot, Nick, and thanks for giving me the opportunity to speak here. I have to be honest, it's very nice to see IX going from strength to strength, right? I mean, there is a group of faculty growing and very, very determined, and then there is the Schmidt Fellowship Program, which is very exciting. And next year, there will be also a master offered here on AI. So it's really growing, and it's really a fantastic initiative. So I'm very happy to be here to talk a little bit about what I've been doing in the area of machine learning, in particular in this domain known as model-based deep learning. So first of all, let me give you an idea of what I do for a living. So most of my activity is around images and is about extracting information out of several image modalities or just enhancing images which might be corrupted. Okay, so I look sometimes at natural images. So here, the acquisition process is quite standard. It's a normal, for example, camera, but there might be various forms of distortions, and then we try and enhance this distorted image. But we also look at different type of applications where the imaging techniques involved are actually much more complex. I work a lot with museums, and in that case, we look at old masters' paintings, and in that context, we use various forms of imaging modalities and try to combine them to extract information of the painting, the material, layers of the painting, and so on and so forth. What is interesting is that the data here is very often high-dimensional, and also there's a large amount of data. Okay, we talk very often about terabytes, for example, of data. Another context in which I also work is in the area of microscopy, with a specific application, microscopy for neuroscience. This is in collaboration with neuroscientists. And here we actually do build our own microscope, and then we try and run algorithms on the data produced by the microscope to extract essentially activity of neurons, obviously of the brain. Now, the first high-level conclusion that I can draw from this type of experience is that the imaging workflow is getting more and more complex. Okay, new imaging methods become extremely complex, and so because of that complexity, it's not really possible anymore to think of the acquisition process and then all the computation that comes after that as two completely separate entities, and instead we need to look at them jointly. So we need really to think of imaging as a joint sensing and inference model. This area that tries to look at the entire pipeline, if you want, jointly, we call it computational imaging. And I like to kind of show these slides, and the idea is that we have the real world, which is continuous, real phenomena, and there are several disciplines that help us to understand the real world. Probably mathematics and physics are kind of prominent, but obviously biology, chemistry are also extremely important. I'm sure there are chemists here or biologists. I don't want to offend anybody, right? But in some sense, we rely to that. Now, in the past, then we would get some data with some acquisition devices, and then we would just derive some computational algorithm on the data, completely forgetting about where the data is coming from. And the idea of computational imaging is really to be at the interface between these two domains, the analog and the digital domains, and trying to look at both domains kind of jointly. Now, key to achieve that, really, is to develop the right interplay between data, or if you want, data-driven methods, and, let's say, the physics of the problem. And in some sense, approaches based on physics or models, which is what we tend to use in the past, have some advantages in the sense that are more interpretable and predictable. Normally, we can predict what the algorithm is going to do, and sometimes can reduce complexity. That's the point I'm going to stress again later on. If we can see that the problem is very structured, we can use that structure actually to reduce the complexity of the algorithms involved to solve that problem. Data-driven approaches are able to handle much more complex settings. So the sad reality for people like me is that the models that they've been developing over the years are just too simple. Okay? If we could develop sufficiently complex models, nobody would talk about machine learning, right? Because we would have solved that. We would be able to synthesize images, let's say, deterministically, right? We cannot do that, and that's why we rely a lot on data-driven approaches, because these approaches learn through data things that we are not able to model with our models. Okay, but in reality, we would like to try and get the best out of these two worlds, okay, so that we get a little bit of maybe interpretability, a little bit of reliability from the model-based approaches, but then we try to use data-driven methods to handle very complicated things. I like to show these slides. This is was inspired by a talk that Stefan Malak gave a couple of months ago. But here are two famous philosophers of, obviously, the ancient Greece. On the one side, we had Plato, and Plato was an idealist. And so he's really the guy about priors and models. Okay? According to Plato, we had in our brain already an idea what is a perfect shape, what is, I don't know, a beautiful landscape, and so on and so forth. And when we see things, we would relate to what we already had in our brain. So it's all about models and priors. So he's really, a model-based guy. And in this famous painting of Michelangelo, right, he's pointing to the sky. And that's not by chance. It's because it's this idea that there were priors that we all have. And then on the other side, we have Aristotle. And he is instead an empirist. So nowadays we would say he's a data-driven guy. Okay? So for him, knowledge comes out of experience. Okay? And so everything comes out of data. And obviously, it is incorrect to simplify things in this way. But I like to say that up to 10 years ago, we were all doing Platonic stuff, okay? And then over the last 10 years, we have all become very empirical, maybe too empirical. We started to just rely on data to solve everything. And really, our goal is to find the right balance between these two different philosophies. Okay, let me try now and dig a little bit deeper on the problems I try to look at and then try to see what we can do, okay? So essentially, the idea is that we're trying to extract some information of an object of interest from the data. So the data that we observe is the data Y. And how do we find our object of interest X? The idea is quite intuitive to some extent. We try to find an X, which would be our clean image or the source that would explain our data, in a way that X must be consistent with our measurements. So if I find my, let's say, object here, if I were to apply the image formation process again on X, I would like to see something relatively similar to my measurements. Okay, that makes sense. It's a consistency type of constraint. And then I also have a prior, right? So if X is an image, let's say a natural image, I would expect that what I reconstruct should look like a natural image, right? And so I want something consistent with my measurement and something that is consistent with my prior, which is, for example, natural images, okay? It's a quite intuitive trade-off, to be honest. It makes sense, but actually, if you want, you can give it a statistical interpretation, okay? So if you assume that your data Y here is corrupted by additive Gaussian noise, then this guy here is a maximum likelihood estimator, and then if you combine it with a prior, this is a map estimator, so it is a maximum a posteriori estimator, okay? I'm saying that for the statisticians in the room, right? I like this more intuitive idea that really I'm trying to get some consistency, and then I want to get something that makes sense, okay? And I like to think of this trade-off that way. But there is a logic behind this trade-off. So where are priors, physics, models going to help us? On the one hand, this maybe can help us to model H, okay, the formation process, obviously, but they can also tell us something about the prior, okay? So we can use a little bit some form of modeling to help us describing the prior, but also the physics maybe to help us describing H, okay? But then probably we want to try and solve this problem using data, all right? So let's try and see how we can combine that. And there are two kinds of approaches that have gained a lot of traction over the last 5 to 10 years, which I'm going to describe here. One is known as the plug-and-play approach. And here, the idea is that the neural network is used just to regularize your problem, okay? Not to solve the problem, but to regularize it. So I'll give you an idea of plug-and-play, and then I'll tell you the type of research we've done in this area and how we connected this regularizer with a specific theory, which is known as wavelet theory, and a specific type of network, which are known as invertible neural networks. And then I'll look at the second approach, which has been used, again, to embed priors or models into a neural network, which is known as the deep unfolding approach. And in here, the way in which we embed priors is by imposing a certain type of architecture to the network, okay? So the deep unfolding technique gives you a kind of a systematic way to design the architecture of your neural network so that certain priors are going to be satisfied. And then you train the network using data in the usual way. So these are the two types of approaches. For this one here, I'll show you some numerical results on natural images. For plug and play, for deep unfolding, we'll get real. So we'll look at paintings and we'll look at neurons and activity of neurons. Okay, so that's the idea. It's about half of the time for each of them. Let me start with the plug and play. So let me give you an idea of where plug and play is coming from, okay, through a kind of a high-level derivation. So remember, we have this problem here, okay? And then the difficulty here is normally the prior, okay? Now, I'm assuming that my acquisition process is a matrix here, so that is kind of simpler to handle, so it's a linear distortion. The difficulty is this prior, because this prior could be something extremely complicated. And then if I have to minimize something extremely complicated, I don't know how to do that, okay? So then the idea is that because the prior creates a lot of problem, I first of all try to separate x in these two constraints. So I introduce an auxiliary variable here. But I say I need to minimize this, but I also need to make sure that x and ni are the same. And when I have a constraint, I can kind of relax it and turn it into a penalty. And that's, again, kind of intuitive. I'm minimizing this guy, and they are kind of independent, but also saying x and ni should be kind of close to each other, okay? So concentrate on x, then concentrate on ni, but also make sure that the two guys are relatively close to each other. The advantage of splitting the problem in this way is that now I can optimize the two things iteratively. So I can focus only on x first. If I focus only on x, then I just have to focus on this term and this term here. And actually, mathematically, these are much easier to handle, okay? Because these are both, in this case, linear terms. So you can actually solve them in one line of code. Let's put it this way, okay? It's quite simple because these are two L2 norms, so it's something quite simple. And in some sense here, the idea is that think of H just as something that introduces blur in your image. Here the idea is to say, okay, first of all, try to remove the blur from your image, okay? And forget about priors, etc. Okay, so you remove the blur, you're going to get something that is probably an image plane with many artifacts. So now that you have optimized on X, let's optimize on V in the hope of removing the artifacts, and then you iterate, okay? So that's the idea. Now, the interesting thing is that if you try to optimize on ni here, then you have to optimize only these two terms, okay, which are shown here. And now, mathematically, this guy here is a so-called denoising problem. So it's equivalent to the problem where you have an image, you have additive Gaussian noise on the image, and you try to remove the noise, okay? So that's exactly equivalent to that. And so now this problem you can solve using, for example, a neural network, because that would allow you to create the arbitrary prior that you want. So the idea in plug and play is to say, use any standard method that you know to solve this line here, but then use a neural network to solve the denoising problem. So go home, create a denoising algorithm for images through a neural network, do supervised training, whatever, do this network as complicated as you want. But then once you've done that, you can solve an inverse problem, essentially, by iterating between solving something kind of simpler with standard techniques, and then the complicated bit, you ask the neural network to solve that for you. Okay? So the interesting thing is that this idea works actually quite well in practice on a variety of inverse problems. Okay, it's been quite successful. That's why it's gained a lot of momentum. The original idea is more than 10 years old, actually. But because it has gained a lot of traction, there have been a lot of results in the area. Here, there is a nice overview paper on the topic that appeared very recently. So what we try to do here is we try to develop our own denoiser. Okay? And the way we develop our own denoiser is also model-based. A denoiser is a neural network, but it's a neural network that we try and make sure that does something that we understand, okay? Which is based on some previous knowledge. And so our idea is that we want to leverage an old transform, which was very popular 20 years ago, which is known as the wavelet transform. It's a transformation broadly used in image processing in particular. And the property, what is interesting of this transformation is that if you have an image and you take the wavelet transform, this is what you have. These are the so-called wavelet coefficients. And essentially, the transform is able to give you a very compact description of your image. We say the wavelet transform is able to provide a sparse representation of images. And I think we can visually convince ourselves that they make sense, because in here, in this small guy here, we have most of the information of the image. And then all the other coefficients, which we call the detail coefficient, a few of them are large. All the others are very small or even equal to 0. And to reinforce this intuition, if I set to 0 92% of these coefficients, okay, so I keep only 8%, right, and I try to reconstruct, I have something very close to perfect reconstruction. Okay? So the wavelet transform has been able to compact the information into a very small number of large coefficients. Now, this is what people think is the reason why this transformation has been very successful in image processing. For example, the image compression algorithm JPEG 2000 is based on the wavelet transform because it is more effective than other transforms that were used before. So the idea is that, OK, we want to use this type of idea to develop our denoiser. Before I do that, let me say that because of this specifying ability of the wavelet transform was very popular for denoising. Okay? So first of all, the wavelet transform is implemented iteratively. So you first do one decomposition, we call it one scale, and then you repeat the process on this version, the so-called coarse version of the wavelet transform. If you want, you can repeat it many times. Okay? But I'm going to focus on two scales as here. The other thing is that, as I said, we call these the coarse coefficients, and everything else here are known as the detailed coefficients. And I'm going to use this type of jargon later on. That's why I mentioned that. But because of this sparse representation, one can do denoising for the problem that I mentioned very easily, because imagine you have your image with additive noise. Then you take the wavelet transform, and then most of these coefficients, if there is no noise, will be very small or close to 0. Right? If there is noise, then they will be corrupted by noise. So what you do is something very simple. You say, let me shrink, so let me set to 0 all the small coefficients, and let me keep only the large coefficient. Large coefficient have information about the image. The small coefficient will have mostly noise. It's a very simple idea. It's also a very old one, actually, but it's very effective, OK? So that's a very simple example. This is your noisy image. You take the wavelet transform. You can see there are a few large coefficients. They are mostly due to the signal. And then there are small coefficients, which you can see now kind of ondulate because of the noise. So you set to 0 all the small coefficients, and then you apply the inverse wavelet transform, and then you have kind of removed the noise. Okay? Extremely simple, and that's because this transformation has these sparsifying abilities. Now, the reason why we revisit the wavelet transform is because we can use it to connect it to a specific type of neural network, which is known as invertible neural network. Okay? And the invertible neural networks has become kind of popular over the last few years. And I'll give you an idea of why people got interested into that. So first of all, the idea of the invertible neural network is that you create a mapping between a set of data, X, this could be images, into another domain. Okay, and this could be what people would call latent variables. And you make sure that this mapping is perfectly invertible. So from X, you go to Z, but from Z, you can go back to X. So why people want to have this perfect invertibility? The idea is the following. Imagine that X are images, OK? And then imagine that you take one image and you think of it as a point in a very high-dimensional space. And now you try to sketch all these points. So you take all your images and you try to see where they are in this large dimensional space. Because images are very structured, right? It's a natural image. It's not something completely random. If you were to visualize that, you would see that they have a strange structure. Okay? They would lie in what we call a manifold. Okay? And so the idea is to say, OK, so I start with this manifold. Right? Let me try and do a transformation so that this manifold is converted into something which is a little bit different. And it's equivalent in some sense to having a vector where each entry is completely independent to the other one and is probably distributed as a Gaussian random variables. Okay? So that's why this process sometimes is called the normalizing flow, because you kind of take something with a very complicated structure, and then you convert into something which is kind of simple, because you can think of it as a vector X, where each entry is, all the entries are independent and distributed like Gaussian. Now, if your mapping is perfectly invertible, that means that now you can take a random vector, apply the inverse, and that will give you something which is distributed in a way which is consistent with a natural image. So the intuition is that this will give you a way to synthesize images, right? Because when you do the inverse here, you take a random vector, you apply the inverse, and that should give you something that is close to a natural image. So that's the reason why people were excited about invertible neural network. We got excited about invertible neural network for a completely different reason. The reason is that you can implement this network through a scheme, which is shown here, which is known as the lifting scheme. And the idea of the lifting scheme is that imagine this is maybe an image or a signal. You split it, okay, into two components, maybe the even and the odd components. And then you apply a network to the even component and combine the output with the odd component. And then you apply another network here, U, to what is coming out from here. And you apply this to the even component. Okay? This can be a super complicated network if you want. And also, you can repeat the process if you want. Right? So you can have another P here, another U, and so on and so forth. Now, because things are done sequentially, okay, by construction, this architecture is perfectly invertible. Okay, you can pick whatever P and U you want, but actually, so this is what you would get, this S and D. But then if you just apply the same set of operation in the opposite order, and then you just change the sign here and here, you go back to the original signal. Okay? So invertibility is just in the structure, which is quite interesting. Remember, you're free to pick P and U in the way you like. Because you're doing these things sequentially, if you apply a U here and then a P here and then you merge, you get back your original signal. So this architecture is perfectly invertible. What intrigued us is that if you want to implement the wavelet transfer, you actually tend to implement it using the lifting scheme. Okay? And that's something that we knew 30 years ago, but we never thought about invertible neural networks. Okay? There is a famous paper that dates 97, where the lifting scheme is used to implement that wavelet transfer that I mentioned before. Now, in the case of wavelets, these two operators, P and U, are linear operators, so are simple type of operators, and also they are fixed. They are not learned through data. They are fixed because the wavelet transfer is fixed. It's something that you design using priors if you want. Okay? So in the context of wavelets, P and U are fixed and also are linear, kind of something very simple. Right? But we know what they do. Okay? So P is called P because it's like a predictor. So you get the even component, and then you try to predict the odd component using this operator P. And if you do a good prediction, here the error will be sparse. Okay? So the error will be mostly zero coefficients. So what you have here is the equivalent of the detailed coefficients that I mentioned before. If you have some error here, then you use this error to update this sequence to make it a little bit smoother so that you can do a better prediction at the next stage. Okay, so that's the idea. And so what is interesting, again, in the wavelet context is that these guys are fixed, but we know what they do, okay? We can interpret precisely what they are doing. So based on that, the idea now is to say, okay, let me use the power of invertible neural network, but also what we learn of wavelets to try and design an invertible architecture here that looks a little bit like a wavelet-like sparsifying transfer. But now we are much richer because we can use neural network. So this will be a non-linear, much more advanced transformation. But my hope is that it can do a much better sparsification than before. So what we do is we replace P and U with now two neural networks, okay? And we learn them through data. When we learn them, we want to make sure that P acts as a predictor, right? Because we want to do the same thing as wavelet, right? But now we can have a much more powerful predictor because this is a network, okay? And so our hope is that this guy will really be very close to zero, so that all the information is really pushed into that small number of coefficients, because that means that probably we can do much better than we've been doing so far. So how can we induce that? How can we make sure that this guy behaves like a predictor? We create a bottleneck to impose that sparsity. And we do that through a denoising process. So first of all, that's the kind of architecture. We have an image, we split it, and then we alternate between prediction and updates. We maybe have several of these things, okay? But then when it comes to train, what we do, we create as input a noisy version of our image, and as output is the clean image, okay? And then our neural network will split the image into something which is a little bit like the coarse version and all the details, and then we introduce a bottleneck here. We denoise these details. So we kind of set to zero some of these coefficients. And then we use the invertible part of the neural network here to reconstruct the clean image. So we have several noisy images, several clean images, and we use all these to train our invertible neural network. Because these coefficients are kind of removed, and given that this is noisy and we want something with no noise, the network will be forced to push all the information about the actual image into the coarse version, and all the noise into these details, which are going to be then removed, okay? And so in some sense, if I go back all the way here, I'm going to shrink these coefficients, and so really I'm forcing this guy to predict the clean part of the image very well, okay? And so I'm really forcing that all the information about the original signal is gradually gathered in here. So that's the way we do training, okay? So we take this noisy and noiseless pair, and then we create this bottleneck, right? So that the network learns to produce directly the clean image, or in other words, to make sure that only the noise is removed by the network. Remember, before I showed you two levels of the wavelet decomposition, and here we can do the same. So we would have one level here, okay? And then, as we said before, we do denoising. Think of this as that coarse version, then we repeat it. Okay, we repeat the process, so we do a second layer, and then we do the same thing and denoising on the details. And if you want, you could do that more times, but 2 decomposition is probably good enough. And then we use the invertible part to reconstruct the clean image. Okay? So we do this for training. Once we are done with the training, we have our, let's say, invertible neural network. Now that's fixed. We expect it to behave a little bit like a better wavelet, but it's a kind of a wavelet. Once we've done that, we can now take a new image, a test image, with noise. And then what we just do, we do this decomposition, we do the thresholding, and the expectation is that obviously we'll produce a clean image. Because everything is kind of predictable, the other thing that we can do, we can adapt some of the thresholds based on the level of noise here. Because we know what these thresholds have to do. So what we actually do, we estimate the variance of the noise here, and based on that, we adapt the thresholds in here and in some elements of the network. And again, this kind of adaptivity comes because we more or less understand what the network is doing. So here is where we gain something by having a model or an idea of what we'd like the network to do. So here are a numerical result that I wanted to show. So these are the noisy images. These are the clean images. When we published this paper, that was probably one of the best denoising algorithms. Given how things advance very quickly, I'm sure there are methods which are much better than this. But I think the main thing I want to highlight is that if you look at the images with the green box, okay? So these are the denoised image. This is a test image, but these are denoised on noise that we have seen in training, okay? So this corresponds to variances of noise that we had seen in training. Whereas for all these other images, this is unseen noise, okay? So it's much larger than what we have trained our network, and yet we have kind of a consistently good result. We don't see, the performance to collapse, okay? Which is something that can happen. That's in part because, as I said, we can adapt the threshold, and we know how to adapt that because this is a little bit model-based. So that's one of the potential advantages of doing model-based approaches, that you can sometimes generalize better because you know how to adapt bits and pieces of your network. Now we can use this in the plug-and-play type of idea that I mentioned at the beginning. So imagine you have a blurred version of your image plus noise, okay? And you like to get your clean image. So what we can do is what I mentioned before. We apply a standard method, for example, linear filtering, to remove the blur. And then we apply the denoising algorithm to remove the noise and make sure that we have something that looks natural. Okay, so this is what's happening. So we take this guy. First, we remove the blur, and then you can see there is a lot of noise. Then we apply our algorithm to remove the noise. Then we resharpen this. Okay, so we have a better image, but more noise. So we reapply the algorithm with a different threshold, and we get this. And you iterate a few times, and eventually you converge to something which is noiseless, more or less, and sharp. All right? And that's really based on this plug-and-play type of idea. Okay, I want to say a couple more things on this topic, and then we'll move on the unfolding technique. I'm very intrigued with this invertible neural network. I cannot deny that. And I think the other thing that is interesting is that they can be used, I think, in combination with some of these foundational models, like, for example, diffusion models. And the idea is the following. So the invertible neural network has a forward part and an inverse, right? So what you can do is to say, OK, the forward part should give me this consistency. So if I reconstruct something, I want to apply the forward part of the invertible neural network to get consistency with y. And then when I then use the inverse part of the network reconstructs x. And then for that, I want to do a correction to get an x which is consistent with my prior. And there I can use diffusion model. Because the two bits are linked, because I have perfect reconstruction, if you adjust one, you are also adjusting the other one. And so you kind of gradually satisfying both conditions here. So this is the idea that we like. So we try to implement it using diffusion models, okay? People talk a lot about diffusion models, so I'm sure you're familiar with that. But one particular model is the so-called denoising diffusion probabilistic models. And essentially, they are trained, this network, in a way that after training, if you create a random patch, okay? So a patch where each entry is random, then the system can gradually, okay, kind of remove the noise. It's a bit like denoising, and then create something that looks like a natural image. And if you create a new patch here, so if you take a different random patch, the system will do the same thing but create a different natural image. And it's quite remarkable that they can get something that looks very natural. Okay, so this is one example, but you can get plenty of other examples. So we tend to say they are very good at sampling from the prior, right? So in the sense that you give them this, and then they gradually get something which makes sense given the priority should be a natural image. It's very remarkable. Obviously, this system has 1 billion parameters, so on and so forth, so they are huge, okay? But then the idea is that, okay, why don't we try and use this to solve the inverse problem? Now, the inverse problem is more complicated because here you are completely free, right? I give you this, and then the guy generates whatever, an image. For an inverse problem, I need to make sure that what is generated is consistent with my measurements. I cannot generate an arbitrary image, okay? If I'm doing MRI, I mean, Shen is there, she's going to kill me. I mean, you cannot generate a random image, right, of an MRI, okay? So we need to kind of impose consistency. And so the idea for us is to do the following. Okay, let me train my invertible neural network. First, I train it, okay? So that's the forward part. And so what I do, I assume I have access to clean images, let's say, and corrupted images. And then try to make sure that what we called the coarse version before is consistent with the corrupted image. So here is the clean image, and I train all these parameters so that the coarse version here looks like the corrupted image, okay? So that's at training. I need to have a data set of ground truth data, okay? But this is what I do at training. Once I've trained my network, I combine it with a diffusion model, one that comes from OpenAI or whatever, right? So as you know, the diffusion model, you give the diffusion model a random patch, then the diffusion model starts to clean it, okay? And start to get closer to something that will look like a natural image. So what we do, we plug this in here and apply the forward part of the network. And now, if this was the correct solution, this guy here would be very close to my measurements. Okay, that's the idea. Because here I'm modeling the image formation process. So what I do is to make sure that this is happening, I replace it with my actual measurements. Okay, so these are the actual measurements that I now have of my image. And then I reconstruct my invertible neural network. So that will give me something here which is consistent with my measurement, but now it's not going to look like a natural image. Okay? So this guy here is plugged back in here. Or in some ways, I take what I had here, and I kind of push it a little bit in a slightly different direction to make it more consistent with this. So I have a gradient step that says, look, this guy is not giving me something sufficiently consistent, so I adjust all this value so that they are a tiny bit closer to what I think is consistent, okay? And then we say, okay, now keep denoising, right? So we do a few more iterations, and then we take what we have here, we plug it in here, we impose consistency, and so on and so forth. So imagine like the diffusion model moves in a certain direction, it's free, and while moving, we push it in another direction gradually, so that hopefully we gradually end up with something consistent with our measurement and that looks like a natural image. Okay, so that's the idea. The whole thing is quite simple because all the complexity is in the diffusion model, and we use existing diffusion models. Now, here are some examples of the results. In most contexts, we do extremely well, actually. And here is a successful example. So this is the degraded image that we have access to. We have the ground truth, obviously, in this case. I mean, this is a hard degradation because there is blurring, there is downsampling, there is huge compression here. So there are also compression artifacts. This is what we reconstruct. Okay, so that's quite good. So thumbs up, all happy. And in many cases, we do well, but not always. Okay, so here is an example where things don't go exactly to plan. So that's the degraded house. Our system reconstructs a fantastic house, supernatural. There is only a little problem. It's a wrong house. Okay, right? If you look at it, obviously, all this is not there, right? Okay, this is known as AI hallucination, right? So when the AI systems start inventing things because they cannot find the answer. And so and actually, this is an extremely interesting topic, is how you control that. There are cases where you don't want to control hallucination because that gives you creativity. There are other cases when you solve serious problem where you need to control it, okay? Obviously, there must be some bias in the data sets. We are investigating that. I think it's a very interesting topic, but I wanted to give you an idea of how you can combine, let's say, diffusion models with invertible neural network. So let me draw the first set of conclusions here, and then we move to the second part on unfolding. Let me just say a couple of things. I think, as I said, INNs are very interesting, especially if one tries to maybe combine them with some foundational models. I think they are more interpretable, and also the architecture are quite simple, which is good, and have some ability to generalize, which I think is good. OK, so now that was on natural images, so kind of not very serious, right? We are now going to get real, OK? Now we are going to face real problem, as I said before, in the area of art investigation in neuroscience. Here we have complex problems. We have experts in the area, judging us. So that's the game. We are raising the game here, OK? But I want to use that as an opportunity to introduce this other idea, which again is very popular in my area, is this idea of unfolding, which is a way, as I said before, to embed priors or models into the architecture of the network. So the idea is the following. Think again of that inverse problem, right? We have these two terms, the fidelity terms and the prior and so on and so forth. And maybe you have some way to model everything, and you're trying to minimize that function. It's something complicated. So normally what happens is that you find an iterative algorithm to optimize that function, okay? So you iterate step by step, maybe you simplify, but that's typically what we do, okay? So in some sense, the idea is that you have your measurement y, you have a first guess of, let's say, your image, and then you apply a certain functional, a certain algorithm, okay, one iteration to kind of get the new version of your image given the previous one, okay? So you start with x0, you plug x0 in here and y to this operator, and that gives you an improved version of your image, let's say x1. And then what you do in a standard iterative algorithm, you kind of go back. You go in circle, right? So you have x1 now, it goes back here, and then produce x2. You go back, x3, and at a certain point after k iteration, you are done, right? But in some sense, you're going in circle, okay? And the idea here is to unroll your iterative algorithm or unfold it. So rather than kind of going backward, you go forward, okay? It's a kind of intuitive idea. So what you do, you say, okay, I have, let's say, first estimate x1 using f. Now, rather than going back, I go forward, and I start thinking of each of these as one layer of a network. Okay? So that's the idea. Because it's an algorithm, okay, there are some steps, the derivative, sum, whatever, multiplication, so on and so forth. So you can describe this with one layer of a network. So you have one layer here, you get the output that becomes the input to the next layer, and you do these k times, okay? So that, and you pick the k you like, so that you have created a deep neural network, all right? Now, the architecture of the network depends on f, and f depends on your optimization, which itself depends on your model. So in that sense, you are embedding your priors into the architecture of your network. Once you've done that, then you just need to train these parameters now. They're not fixed anymore. You train them and you learn them using, for example, standard supervised learning if you can. So you have a data set of clean images, you have your measurements, and then you do standard backpropagation and so on and so forth. Once you accept that you're going to learn the parameters of each of these functions f, you can also allow each parameter at each layer to be different, and so you may end up with slightly different functions at each of these layers. So you have ended up building a relatively complex neural network, but remember that the architecture is really model or physics driven, okay? If you're not fortunate enough to do supervised learning, then what you need to do, given your estimated x, you mimic the image formation process again so that you get the data again and just try to impose that this guy here is as similar as possible to this one here. It's a self-supervised type of approach, which you need to use very often for real problems because you don't have the data, okay? But so that's the idea, and again, is an idea that has gained a lot of traction. Now, in this talk, the kind of model that I'm going to use is, again, this idea of sparsity, okay? I'm going to be a little bit more general. So before, remember, the idea was that this is an image. And imagine that these are the wavelet coefficients. As we said before, the wavelet coefficients, most of them are close to 0. So you can describe them with a vector with only a small number of non-zero entries. And this would be the inverse wavelet transform. Is linear, so you can describe it with a matrix, okay? You can go a little bit beyond this simplified model and then say, okay, let me replace the wavelet with what we call a dictionary, right? So you are going to have a lot of possible bases, if you want, a lot of possible functions. And so this becomes something fat, and we call it a dictionary. But what you want is to make sure that this vector is sparse, okay? So that's the idea. And the idea is to say, okay, I can, given an image, I can always describe it using this dictionary and using a sparse vector, okay? You can now learn this dictionary if you want through data, okay? Let's assume we have D. Okay, so the question is, if I have an image, how can I find this sparse vector? It's not a straightforward problem. And there is an iterative algorithm to do that, which is known as the iterative soft thresholding algorithm. And that says essentially, given a preliminary sparse vector, you update it using this step here, which is a gradient step, essentially, okay? And then you apply a nonlinearity, okay? A nonlinearity is a soft threshold here. That means that you shrink all the small coefficients, okay, to 0. In this case, you look both at positive and negative. So it's different from ReLU in the sense that if you have a coefficient which is large in amplitude but is negative, you keep it, okay? So that's a soft threshold operator. So actually, one can prove that under certain condition you converge to the sparse representation and so on and so forth. Okay, so that's the way you can do that. So what you can do now, you can write this using a block diagram, which is highlighted here. You have your first estimate of the vector. This is your image. And then here you implement what is in there. And this is the nonlinearity. Okay. If you want to do the unfolding, then here is the unfolding idea. Now you have one step after the other of this same architecture. So by construction here, and now you learn the parameters, okay, by assuming, for example, that you have access to images and the correct sparse representation. By construction, this architecture would find, once trained, always the sparse representation. Again, this idea is not particularly new itself. It was actually introduced by Jan LeCun 14 years ago, 13 years ago. But as I said before, so Jan LeCun focused on the sparsity, so what I have shown here. But then you can have different type of optimization and therefore different type of architectures. And again, it's an idea that has gained a lot of attraction. And this is an overview paper due to Jonina, Eldar, and co-authors in case you are curious about the topic. Let me show you how we use this idea in two very different problems. Okay, one is in the area of art investigation, and the other is in the context of neuroscience. To give you the idea that it's actually an idea that is potentially transferable, which I think is something quite interesting. Okay, so the first context is art investigation. So as I mentioned before, because this is work in collaboration with the National Gallery. So these people analyze old master paintings using different imaging techniques. Here is an example of X-ray, okay, a simple example. And as you can see from the image here, underneath the visible image, there is another image, okay? You can see a gentleman here, okay? And actually, this is relatively common, especially at that time, for various reasons. First of all, an artist would paint and then would probably change the type of painting that they want to do for various reasons. And obviously, you cannot erase what you're painting. The only thing you can do is you can paint on top, right? And therefore, you start creating several layers, and there could be something underneath, okay? For example, it's quite interesting. We looked at the Duke of Wellington painting, again, due to Goya. And then the problem for poor Goya was that he was doing this portrait of the Duke of Wellington, and then halfway, it was almost done, and then the Duke of Wellington has to go to some war, right? I mean, there would be a war every few years, right? So he goes to the war, he wins the war, comes back with new medals, right? And so the poor Goya had to paint on top of the old medal, the new medal, and so on and so forth. Then he changed actually apparently the color of the jacket, and so on and so forth. So you start having a lot of layers, and you would like to kind of discover what is underneath. But also there are other cases. Canvases at that time were very expensive. So an artist would try to save money by painting on top of an old painting, something that happened here. And obviously a famous example of that is Van Gogh. Van Gogh was very unsuccessful during his lifetime. So he was very poor. So he would paint something, and then he would not sell it, so he would paint on top of it. Some people think that up to 50% of Van Gogh paintings have another Van Gogh underneath it. I'm not sure how reliable is this statistic, but it's quite remarkable if you think of it, okay? There are a good number of Van Gogh paintings that we can discover. But essentially, we are faced very often with this type of demixing problems. And so what we'd like to do, if I think of this case here, we'd like to get two different X-ray images, one linked to the lady, okay? So one linked to the visible image, and the other linked just to the guy underneath. And so what we want to do, we want to use the visible image as kind of side information to help us. So the intuition is that, okay, the X-ray of the lady and the lady herself, Isabel, the visible, should be correlated in some ways, right? Whereas, obviously, the gentleman and these other two paintings should be completely unrelated. It's quite intuitive. The question is, how am I going to model that? So we model this using this idea of sparsity. So first of all, we start by saying we assume that the visible image and all the X-ray images have a sparse representation. So we can find this dictionary so that everything is described with a small number of parameters. And then we say the visible image and the X-ray of the lady share the same sparse representation. Okay, to use a language of now common is like saying they share the same latent space, right? So mathematically, it's described here. These are the two sparse vectors. So this is the X-ray of Donna Isabel. This is the visible image. We expect that the sparse vectors are in common. So that's kind of our model. The other assumption is that the two X-rays share the same dictionary, so D. And that's because they're both X-rays, OK? And so the dictionary is the same. The sparse vector is different. And so we impose that in here. OK, this is in common. So that's our model. And then we add a couple of more things. OK, we assume that the measured X-ray X is the sum of the separated X-ray. This is actually physically incorrect, but we saw that it worked well anyway. Okay, we tried to use a more sophisticated model, but in the end, the result was the same. Okay, so that's not completely correct. We should have taken the log of this, but at the end of the day, it's good enough. So this is our model. Now we have the model. How do we create the neural network? Well, the neural network, given that model, you have a kind of a complicated optimization problem. Okay, as before. There is one term that we added here, which is known as the exclusion loss. So here we are making sure that given the two X-rays, if I were to extract the contours of the two X-rays, and I take kind of the product should be close to 0. So the two contours should be very different because these are two different images. It's known as the exclusion loss. So essentially, we optimize step by step here. We fix one variable and we optimize the other. But as we mentioned before, that will lead to an iterative optimization algorithm. And then what we do is we look at the algorithm, and then we convert it into a layer of a network. Okay? So we end up with this single layer. It's a little bit complicated. I mean, it looks complicated. It's not complicated, but obviously there are all these connections here. But I think the message is we have an assumption. We create a model. Given the model, we come up with an iterative solution. And then rather than solving that, we use that to create a network. So this is one layer. Then we have several layers. And then we do a training. This is self-supervised learning because obviously there is no ground truth data. But anyway, this is the result we end up with. So this is the X-ray of Donna Isabel. This is the X-ray of the gentleman. There is still a little bit of crosstalk, but it's a relatively good separation. It's not perfect. It's relatively good. If you sum these two, you get this. And this is the error image, which is very close to 0. OK? So that's one example. Here, I just want you to show you the result because it's kind of fun. This is a different modality. It's known as fluorescence X-ray. So fluorescence X-ray, out of each pixel, you get a signal that looks like this. And if you look at this signal in the energy spectrum, you get a stream of pulses. The location of these pulses tells you which chemical element is present in the painting. Okay? So one of the problems here is that given a painting and given the XRF data, you would like to extract the so-called elemental maps. So something that looks like this, okay? So we have our algorithm, we develop this, and so on and so forth. But what is fun is that when we apply this to this painting of Leonardo da Vinci, the Virgin of the Rocks, okay, then we applied it in here. We looked at the zinc map, and this is what we extracted. Okay, if you look at here, you can see that these are sketches of an angel, right? There is the head here, and there are the wings, okay? And this angel is not present here. So this is actually sketches of a previous composition of Leonardo then Leonardo abandoned, okay? So that was kind of exciting, and then we do that on several panels, okay? And then you can see here that there is actually more complex composition. This is the Virgin Mary. This is the angel that I mentioned before, and here actually this is Christ. And this is where we found this, and you can see that when you compare with the actual painting, these are underdrawings, okay? So this is a previous composition. What the curator made me observe is that in the previous composition, Christ and the Virgin are looking to each other. In the current composition that you can see, obviously, in the National Gallery, is Christ and John the Baptist that look at each other. So actually, Leonardo decided to change the message that he wanted to deliver. We don't know why. Obviously, that's not our problem. The curator are working on that, but it was very, very interesting and fun. OK, I'm going to spend the last 10 minutes on this other application. Yeah, I think I'm on time. And then we'll finish. And again, I'll show you how we more or less do, again, this unfolding type of trick for these very different problems. OK? So this is a problem in neuroscience. In neuroscience, OK, people tend to use more and more often some form of fluorescence microscopy to monitor the activity of neurons. And they do that in vivo. So that means that the animal, typically a mouse, is alive, okay? It is sedated. They take away the scalp, so it's not nice. But the mouse is still alive, okay? Because obviously this is the type of thing that they want to do. And Now, with this type of microscopes, you get this type of data. Okay, you can see that in here. Okay, so these cells are neurons. And when they are brighter, it means that the neurons is generating what is known as an action potential, so a pulse. Okay, and we know that the brain encodes information through these pulses. Okay, but we don't know how this information is encoded, obviously. So what neuroscientists would like to see is a large population of neurons. So they would like to get this type of data, first of all in 3D, not just as slice, but you would like to go deeper, and then on a large region, so that you can monitor simultaneously hundreds or possibly thousands of neurons at cellular resolution, okay? So at the resolution of the neuron. So the best technique to have this level of resolution is two-photon microscopy. The problem with two-photon microscopy is that it is a little bit too slow, okay? In two-photon microscopy, what people do, they have a laser. The laser point on a specific region, and then you scan your region gradually. Now, if you're pointing here, let's say, and there is a neuron there, and the neuron fires exactly when you're pointing to that, the neuron will become fluorescent. Okay, that's because there are some indicators that have been injected into the sample so that the neuron becomes fluorescent if it is illuminated and simultaneously it is active. And that is what we collect. Okay, so that allows this scanning technique to have high resolution, be resilient to diffraction problem, scattering, sorry, and so on and so forth. The problem is that this is very slow because you scan this plane here, then you go down, scan the following plane, and so on and so forth. It is just too slow if you want to go over a larger sample. Okay? So one needs to find a way to increase, in some sense, resolution in time by keeping a similar type of resolution in space. And I looked at different ways to scan the regions. Okay, so for example, you try to scan a plane by plane, as shown here. This is actually quite popular. It's known as light sheet microscopy. But these are still scanning techniques, so things are still slow, right? We would like really to be able to, in one snapshot, to get information about the whole volume, so that we can put here a video camera and essentially get information of the entire volume here at video frame rate. This is what we'd like to do. But how can we get the entire information here? Well, we need to build a new microscope. We need to change the optics of the microscope. And the idea here is that this, in some sense, up to here is a normal microscope. Here is where you have your sensors that collect the light. So this is where the image is formed. Before that, you create this set of small lenses. Each of these is a lens. So you create what is known as a macro lens array. Now, the macro lens array, without going into the details, creates something that looks like having many small cameras. Okay, so imagine you have many small cameras. You take a picture, you move, take another picture, you move, and so on and so forth. Now, if you really take several pictures at slightly different location of a scene, you get 3D information, right? Okay, you get a little bit of information of that. So that's the idea here. This type of technology is known as light field imaging, and obviously this is light field microscopy. So our idea is to say, okay, let's put this microscope, this macro lens array here. To convince you that you're getting 3D information, here I'm showing you the type of image that is formed, okay, because we have a way to model all the process, assuming that your image, your source, is a point, okay? So if you have a point-like source, okay, these are normal lenses, then you have this macro lens system, then you get this pattern. If you change the depth of that source, so you move it here, you get another pattern. If you move it, you get a different pattern. So the fact that you have a different pattern per depth highlights the fact that you can encode 3D information from this data. Okay? It's not immediate, but you can do that, right? So this image, which is a light field image, has X, Y, and Z type of information. This is more evident if you rearrange the pixels here in a proper way, because then you discover that the point is converted into a line, and the slope of the line is related to the depth, okay, of the object. But at least we can believe it that if I create this, if I add this macro lens array, I can get 3D information out of a single image. So based on that, our idea is to say, all right, so now let me create my microscope where I illuminate the entire volume here. I have my macro lens array here, and so at each frame of my video sequence, I have one light field image. So I have the equivalent of volumetric information at frame rate, which is exactly what I want. There are some drawbacks here. It's not always a win-win situation, obviously. First of all, to get that here, you need to trade resolution, right? So you lose a bit of XY resolution to gain a little bit of resolution in Z, okay? The other problem is that you suffer from scattering much more than before. So to kind of and compensate that, we put together these two microscopes. So we created a kind of a multimodal microscope, okay? It's a quite sophisticated acquisition process, which is done by my colleague in the bioengineering department. Okay, I should not get any credit for that. But essentially what we do, you have your sample. We first do a slow scan to get the structural information at high resolution. So it's a slow scan, but we make sure that the neurons are always bright, okay? We can do that, okay? It's not immediate, but. And so that you get high resolution structural information. And then after that, we replace this part here with this part here, change the illumination, and now we do the functional analysis. So we make sure now that the neurons are bright only when they are active, okay? And we take the video sequence. So the hope is that we can use a little bit of this information to enhance our ability to reconstruct the 3D information here, okay? Okay, so the challenge now is that imagine you have your volume, you get a light field, now you need to use a computational methods to reconstruct the volume, okay? And we're going to do that using machine learning. The problem is very hard for various reasons that I mentioned before, but there are also something which is unique to this system, okay? So first of all, the model, okay, the forward model, so the model that describes how the volume is converted into a light field image is essentially linear, which means it's much simpler to describe it. And it's actually structured, and I'll show you in what sense it's structured, okay? And that's very helpful. The other thing is that the data itself is sparse, because if you think that you have a volume, small number of neurons, and they are not active all the time. So if we go back to that idea of sparsity here, we have the sparsity, but directly in the image domain. Because if you think of that of your image, most of the time it's all black, and then you have only a few neurons which are bright, okay? So you already have sparsity in the image domain. And so that's good, okay? That's good. So the problem is very structured for us. So that's a good news, okay? So first of all, let me clarify what I mean by the fact that the forward model is structured. And just show that, let me show that to you through an image. So imagine again you have your point source, okay? The point source will give you a pattern. Now you move the source, you keep the same depth, but you move the source along the x-axis. Okay, so you moved it a little bit, you have a different pattern. But then if you move, and you move by quantity which is equal to the size of your macro lens, then you see the same pattern again, just shifted, okay? So the pattern repeats itself, but not immediately, periodically. So this type of system are called periodically shift invariant. And besides the weird name, from a practical point of view, this is a good news, because that means that if I model this with a matrix, this is a structured matrix. It's actually block circulant. Block circulant means that I can implement that using a bank of filters, or to use the machine learning jargon, I can use one layer of a convolutional neural network without the nonlinearities. Okay? So I can model that with something very simple, and I can implement very quickly. And that's important because this matrix H here has normally 1 million by 1 million entries. These are big matrices because these are big data problems. So we have to face this reality, right? And so here, because of the models, I can see that this is structured, and actually I can implement H transpose, the inverse of H, whatever, using filters, which is something very easy to compute in practice. So that's when I mentioned before, sometimes models help us reduce complexity, right? If you don't model it, this is unstructured. I mean, you cannot really easily solve this problem unless you are OpenAI, but that's not really our thing, okay? So that's the first good news, right? So H is very structured. The other thing is that, as we said before, the volume we are trying to reconstruct is in itself sparse. And so we can do that sparsity recovery that was mentioned before. So I can try and do this optimization using that same iterative method that I mentioned at the beginning. Okay, the only difference now is that rather than having the soft threshold as nonlinearities, I'm back to the ReLU nonlinearity. There is one simple reason why this is the case, is because I'm trying to reconstruct an X, that's the volume, and the pixels in the volume are always positive, right, or 0. Because when you have activity, you have something. If you don't have activity, you have 0. Okay, so you have a so-called positivity constraint. So when you combine sparsity with positivity constraint, the nonlinearity is turned into a ReLU. All right? Okay, so now we use the same trick. We do unfolding, right? So we created the network. So this layer here is implementing this guy is model-based. But also remember that this H here is itself structured, okay? It's a filter bank, as I said before, because we know the physics of the forward model. And so we have all these guys, okay? So we have a few layers, and then we need to do training, right? Okay, so training is a bit complicated because obviously there is lack of data here. So when it comes to training, we have to use a little bit of several tricks to get something good. So it's a combination of, we have a small ground truth data that we can create. So we have small data sets where you have the light field and the ground truth volumes. So we can do a little bit of supervised learning. We combine it with an adversarial network to kind and create a regularization here. So we also train an adversarial GAN here, the adversarial network, and we do a little bit of self-supervised learning. You create the volume, you resynthesize the light field, and make sure that these two guys are together, so are consistent. So we need to do a little bit of everything because obviously it's not that, as in natural images, you produce all the ground truth data you like. Right here, you don't have that. So we can do a little bit of everything. And then we do the training of this network. So let's see what happens in practice. So that's one example on data for which we have the actual volume. So that's the ground truth, one slice of the ground truth volume. These are two kind of standard methods which are just based on model-based, so no learning. And this is our approach, which, okay, perform better, but it's also very fast because obviously once you train your network, then running the network is very easy. Here we extract volume, so you can see different slices of our volume, and then here I'm picking a few neurons, and you can see the activity of the neurons that then we can extract. So we kind of more or less extracting one volume per frame, right? And then we have a video sequence, right? So it's kind of 4D, the type of data that we have extracted, okay? Because we can see then the functional activities of neurons. And here I'm trying to put everything together. So this is more or less the 3D structure of the neurons. You can see that they are kind of firing. Here I collapse the Z-axis so that you can see things getting brighter from time to time. Okay, so given this video sequence of light fields, we create the volumes and the neural activities. Okay, I think I can conclude here. I think, okay, I ran a little bit out of time, but I can conclude here. A couple of things. I believe that cross-fertilization between model-based approaches and deep learning is fruitful. As I said, we tend to use very often these two ideas, plug and play and deep unfolding. And it's quite interesting that they are kind of transferable. They tend to work well, in some sense, in very different contexts. And I think this is quite useful. And the use of models can reduce complexity, might lead to better results. The area I work on is computational imaging. There are a lot of young guys here. My recommendation is that jump on the topics, okay? It's fun, right? That first message is fun. You talk with curators, neuroscientists. I'm talking with biologists lately because we are interested in cryo-EM and structural biology, and so on and so forth. It's interdisciplinary, but also when you start having these complicated, imaging devices, you probably really need, if you want to solve a real problem, you really need to look at the whole pipeline jointly. So I think that's the right way to approach that. I'm done. Sorry, I need to acknowledge some people, okay? Junjae Wang is a former PhD of mine and postdoc, and he's the guy who did most of the work on invertible neural networks. Everything related to microscopy would not have been possible without this group of people. And in particular, Amanda Faust is my colleague in the bioengineering department. She's the brain behind brain imaging, really. She builds the microscope and understands all these type of things. So all credit to her. This is the crowd of people working in the art investigation project. A special acknowledgement to Miguel Rodriguez here, who from UCL, who kind of put together this consortium. Catherine Higgett is our main contact from the National Gallery. She gives us the data and all the information and so on and so forth. And she looks at our results, and she's very critical. And also a special thanks to Ingrid Dobeschi from Duke University. For those who are old enough, I think they know Ingrid Dobeschi, and I think she's as good as it can get as a collaborator. Thank you very much.
That was an amazing talk. Make sure that's recorded. I was wondering if you know the details of the physics of the process, that generates the images. Say it's typical in medical imaging, for example, when you want to reconstruct data that you do. Is there a natural way of embedding that in this framework beyond just considerations about sparsity or symmetry or properties like that?
Yeah, I think the natural way for us is that if you know the physics of the image formation process, you know H. That's the way we will look at it, okay? Now, then one may say, okay, if you know H, why don't you just solve the problem? Obviously, and you know better than me, reconstructing the object, so let's say the image from the data is an extremely ill-posed problem. So you need to put the prior, and then all the things get complicated. But for us, yeah, that's the most natural way to embed priors about the physics of the acquisition process. That's also interesting because if H is linear, we know how to handle that. It's a matrix. But when H starts becoming non-linear, or if you want to try and see some right, then also modeling that starts becoming difficult. So sometimes what we do, and we did a little bit of that with the microscope, is that we say, okay, H is approximately a shift invariant, so we expect this type of structure and so on and so forth. But then we create data where a small data set, ground truth, so the actual volume, high resolution, and the light field, and then we adjust the parameters of the system in the hope that we can catch things that we cannot model. Okay? It goes back to what I said at the beginning. We don't like to accept that, but our model is very simple. Okay? So linearity is good, we can do that, but in reality, nothing is linear. So maybe I start with something linear, I adjust a neural network, create a neural network where at the beginning the parameters would correspond to that model, and then maybe try to adjust the parameters so that I can encapsulate richer information, which I don't know how to describe. Okay. But having said that, the physics is normally directly in H.
Yeah, I agree. Great talk. Thanks a lot. I thought it was fascinating. I have a question about the reconstruction of the art, which I think is a cool application.
Yes.
So in your case, you showed us almost like a binary problem where you had one image and a second image behind, but you also hinted that sometimes they would reuse a canvas multiple times. So if you end up with a problem that's more complex, where you might have 3, 4 layers, is there a way you can resolve this by imbricating your functions, or what's the approach there?
Okay, we'd like to solve that problem, okay? So to have a very nice stratifications, okay? Is also, that's quite interesting, because obviously when we discussed that with the National Gallery, they said it's not possible, forget it, okay? So that's also nice, you know, you have decorators and they're like, you know, guys, take it easy, right? You're not going to solve this problem. We've been looking into this one. Now, so the short answer is that it's super hard, okay? Already for this, the mixing, we struggle, okay? We get something, but we're still not there. That problem is super hard, but if we have more modalities, there is a little bit more hope, okay? For example, the XRF that I mentioned kind of briefly, what happens is that there are some frequencies that can go deeper, okay? And others that don't go that deep. So that gives you a little bit more of that type of information, okay? So for example, the LED, I think for LED you have several lines, okay? LED is always present, so it's something that you always get. But because you have different lines, the response you get is sometimes mostly related to something close to the surface, and another response is more related to what is underneath. So that gives you a little bit more information to try and mix, let's say, more than 2 layers. So it's not completely impossible, but I think we need to be realistic. It's extremely hard. In most cases, we are kind of happy with 2 layers because I mean, I'm not an expert here, but I think it's very unlikely that one would reuse the canvas 3 times. Okay? Maybe Van Gogh has 3 paintings somewhere, I don't know, right? But this is relatively unlikely, okay? But it's a good point. We don't know how to solve that. It's super hard. Okay.
Oh, thanks.
Thank you very much. So it's a very naive question. So just the etiology of this whole, you know, like I'm questioning the idea of using neural networks to solve traditional constrained optimization problems, right? So what are the limitations of, you know, training neural networks to solve these classical optimization problems, right? So when you compare, for example, using a traditional approach versus when you model it beautifully using this computational graph and you try to optimize these, you know, mappings and functions, right? So what are, first, is it like, is it more useful? But I'm sure like you have shown that already, but haven't read this line of work, so I'm new to this.
Yeah, no, sure.
And the second thing is, what are the key challenges when tuning the parameters and training these models to find a good optimum? Yeah.
Okay.
Thank you.
I have an immediate answer. The answer is I don't know. Okay. But now, having said that, there is a couple of things I wanted to mention. So first of all, okay, in practice, this, let's say, unfolding idea seems to work quite well. Okay. Now, one argument is, and sorry if I just go very quickly back to that slide. One argument is that, in some sense, you have created a richer model. Okay, because, sorry, let me try and see whether I managed to go back to this slide here, because the original optimization would say, okay, there is one functional here, and then you do always the same thing.
Yep.
Here you are making it a little bit richer because you're saying, look, you can tune the parameters so that at each stage you do something slightly different, which kind of also makes sense to some extent because maybe at the beginning you're trying to get this sparse vector, and at the beginning you're starting not knowing anything. After a while, you start having something which is close to sparse, and so maybe you want to adjust the parameters, okay? So that's one argument that is used to justify the fact that we often see these approaches to work better compared to just applying the traditional method, okay? So for example, some of these optimizations are based on ADMM. I mentioned that before for neuroscience. Just to make an example, this works better, okay? There are there is one major downside, okay? We cannot prove anything on deep unfolding, okay? As far as I'm aware, there is no way to prove convergence or anything, okay? For the plug and play, there are some results. So people can say something about guaranteed convergence and so forth. Deep unfolding, we really don't know anything, right? So this optimization, you might be able to say something, okay? But for that, we cannot say anything, which means, right, that you may get a completely wrong result and you don't really know why, okay? So there is still an issue, in my opinion, of fully trusting the output that you get, right? Because, okay, we have some ideas because the architecture is controlled, but still there are things that we do not control, okay? So I guess that, I hope it provides an answer in the sense that, yeah, we cannot guarantee anything, so there is really a theoretical weakness there. In practice, things seem to work nicely, okay?
Yeah. Thank you very much. Thank you. That's very clear. Thanks.
Yeah, thank you. Yes, so just to follow up maybe on this question is that if you have k goes to infinity, maybe you can apply theories of shallow networks. I mean, would your framework apply when k go to infinity?
So, okay, right. So now we're going a little bit beyond my level of knowledge. So I think there is a variation of this network, of this unfolded technique, which is called, I forgot the name, where essentially, I forgot the name of that network, where essentially you have something that is equivalent to iterating that things an infinite number of times, okay? I still don't think that they can prove precisely convergent because all these things is so nonlinear, okay, that I think there is still, I'm not aware of precise answer to that problem, okay, to be honest. Now, that goes a little bit beyond my knowledge, I have to admit that, okay?
Yeah, but I see somehow like resonance or shallow networks with infinite width.
Okay.
I don't know. I'm just conjecturing.
Right. So my experience is that you have some nonlinearities there. Yeah. You change the nonlinearities because they can be different per layers, and that all of a sudden makes the problem very difficult to analyze. Okay, and maybe someone has shown something I'm not aware so far. Okay.